Oh, there are two people waiting on me. Sorry. We're just going through a little existential dread. So we can't control politics, can't control the electoral college or anything. Can't even really control dynamics, but we can at least make predictions and see how well they play out. Well, I guess you can, if you have a good model, then you can make a control system for it. So that's not true. We can control it. We're engineers. We can figure out. And I guess that's one thing that we don't really get into this class, 'cause it's sort of like we're laying the groundwork for dynamics. But a lot of people that are like experts in dynamics are experts in dynamics and controls. Like they build a model, and now that you have a model that you know how it behaves naturally, you can add in a feedback loop and now control, like get it to do what you want it to do at any point in time. But that's all like control theory kind of work. Yeah, and I remember when I was an undergrad, I had this control theory class, and the professor, I forget if he worked for like Lockheed Martin or another kind of like aerospace company, but his background was all like control systems for flight and navigation kind of things. And he gave us this transfer function. It ended up being like an 8th order differential equation by time like all the loops, all the forward and all the positive and negative feedback loops were all kind of circled in. And we all followed his instructions step by step and got like the right answer. So everyone got an A in the class. And then the next semester we had control theory 2. It's like apparently not everyone's allowed to have an A in a class. Like the university was like, what happened? Like how did every single person get an A? And they must have like asked someone in the class, like, what did you learn? They're like, I don't know. Like, I just don't know. I think about that guy a lot. About like, did he get in trouble for all A's? Like, what does it matter? What does the university care? They're still paying tuition. Anyway. Last time in space, we were trying to get through part A of just defining where this thing is and how fast it's moving. And after a little bit of like getting stuck, not sure where we were going. I don't know if you agreed with me, but I said we could just call this, like if this is my ER and that's my E theta, I could say its position is just some radius along that ER vector, and then its velocity is an R dot along that ER plus an R theta dot along that E theta. So in terms of like just getting, and that's all kinematics is. It's just like trying to get an equation that represents how, when I look at this thing, where is it? Usually 2 dimensions, we need 2 unit vectors, and 2 magnitudes. I don't know. Did anyone have issues with that part of it? It's okay if you did. It totally makes sense now. Like ah, he wrote up an R on the screen. Now it all makes sense. It doesn't have to. It can still be confusing. Oh yeah, so this was just that O prime. So that's like part A. So if I want to say part B is going to be what is the position with respect to O? I'm going to write something and then just check in and see what you think. Oh, sorry. So I think the position of P in that moving reference frame, so reference frame B is moving constant speed away from reference frame I think I can say the position is V0T along that E1 plus RER, the R, that same position in O prime. And then the thing that I want to check in with everybody, what is that? What is the velocity of PO going to be? So I'll check in. And again, if you don't agree with me, totally fine. You can do it your way. Yeah. Think about it a different way. Yeah. Yep. Yeah. Okay. Yeah, exactly. Even if this were pointing backwards, you can go that way. Still stuck. Position E. What would you want? Yeah. Yeah. Why? What I'm saying is like so at time zero, there's no distance till time L. It's whatever position is here. It's just the position. So I'm taking vectors from here to here, another vector there. So if I add this, what's that? This velocity is how many meters per second. So if I want to know how far meters per second, how many zero. Okay. Yep, that makes sense. Maybe time, when you take that derivative, you're doing MT, time drops out. So it's more a question like if I take a derivative of E1, changing direction. Yeah, but when you're defining like position velocity, the forces that are acting on it don't matter. All you're doing is like creating like a fictional coordinate system. I mean, it's not fictional; it's real to you. You're going to use it to solve things. No, that's a constraint that O prime is always moving at B0. So it's as if it's like on a cart and the cart is just shooting away. Yeah. Okay.
So I was wondering what it means when it's saying spring is traveling in the V1 direction. Is that like the whole system doing?
Yeah, like the whole thing is that whole frame of the moving at a constant speed.
And that's why it's not in the position.
Yeah, exactly. Yep.
And then in the ER term position, does that kind of like give you the angle? So I know it says the spring spring about O prime.
Yeah, so the springs, that ball on the springs moving around, it'll look kind of like an ellipse of an orbit.
Okay.
Yeah. Springed out really far and closer.
And then so is ER why we don't have a theta term in position then?
Yeah, because ER is a unit vector that points along that angle theta. So at least like when I was like creating this definition of RPO, right, I want that one. I was taking those two vectors that go from O to O prime and adding, yeah, O to O prime plus O prime to P, and just saying, all right, the total position, like where it is, has got to be adding those two vectors together. But I'm mixing and matching unit vectors. Is that a problem? I mean, not for now, right? We didn't do any math on it, so as long as we know that the E1 and ER, those are not necessarily orthogonal. They're not 90 degrees to each other. So as long as we keep track of that, it's okay. You can use as many unit vectors as you want. Did anyone figure out what velocity was? Saw some people starting to write it down. And then some other like clarifying stuff that was coming up is like that frame B is just moving at a constant speed, as if like the thing's on a table and you're running the table at a constant speed. And whether or not you need more or less force to maintain constant speed is kind of irrelevant, because it's just saying like it has to move at a certain rate. So I saw this. It's like V0 E1 plus something. Oh yeah, yeah. Just like that. Just take the first vector and add it to the new one. Right? All right. Yeah, yeah, yeah. Okay, nice. All right, cool. So nobody seems sure of their answer, even though they were putting like at least exactly what I would put. That I can take that velocity of the frame plus the velocity relative to the frame, add those together. That's my total like velocity of P with respect to the original like O frame rather than O prime. Cool. And that's part B. Like, so we're checking our way through here, right? And then we know how to draw free body diagrams. For part C, I want to put the reference frames in here too, though. I'm just putting those in for a little bit of bookkeeping, because when we're dealing with angular momentum, not only do we care about what force is there, but also where it's pointing. So we'll take a look at that too. So what does a free body diagram look like? This one you guys are experts in. Yeah. Oh man, what forces are there? Done. That's it. No, actually, yeah, just the spring. It's the only thing touching that part of the key is the spring. So we've been dealing with that by having a free body diagram and a kinetic diagram, because that is the centrifugal force is centrifugal acceleration at velocity. Right. So in the opposite direction. Yeah. Oh, on the free body diagram. Yeah. Okay. as long as you're keeping track. These systems. Cool. Easy. Pretty easy. Almost too easy. Too easy. At least that's what it seemed like when I was asking. Like, what were you thinking? It's like, just force of the spring? Like, yeah, that's it. That's all we need. It's when we're looking, so I drew those two reference frames, because when you look at this, what is the how much torque does the spring create around O prime? Like, what is the sum of the moments around O prime? The force points directly to O prime, right? Because the spring is attached right there. So what's the moment that's created? Zero. Yeah, 0. I'm seeing some like goose eggs. Yeah, 0. So forces that go right through the origin like that, they don't create any torque. There's no torque created. So it's got to be 0. No matter how big that spring force gets, it's always creating 0 torque. Is the sum of the moments around O 0? Like if the sum of the moments in one spot is 0, is it also 0 in another spot? Some head shakes no. Some people waiting for the answer. Check in with the poll locations. Iowa says yes. Idaho says no. Pennsylvania's got a hanging chad. Some of the moments around O is not 0. Like think about the one case. If the spring is pulled straight up, it's definitely creating a moment on around O. Like there's a spring force that is a distance, it's creating torque around it somehow. There's some kind of constraint force to make sure that that frame doesn't rotate, but some of the moments is not 0 for that case. Now we need this little guy. Oh. So I want to know what is, so the moment is not, the moment is 0 around that O prime. That doesn't mean that we have 0 angular momentum. It means that it's constant. So I want to know, what is it? Like if it starts off at a given value, it's always going to be that same value. If it starts at 0, then it's 0 forever. That's the boring answer. We want the interesting answer, the non-zero. So what is that angular momentum? still have to be pulling, have to replace this and that, because we said that this is our definition, right? Yeah, yeah. Yeah. Yeah, so I can take this, plug it right in there. Oh, okay. All right. Yeah, yeah. No, we're not starting from scratch. We're doing it slides. Yeah. Is that how you do it on a cross product? Trying to remember? Yeah. Well, it's essentially electric. Yeah. Yeah, exactly. Yeah, I think you do the ER and K. Third. Yeah, now you have no more? Oh man. Alright, well you have to get the ones down. I know. So like this thing is exactly what this. I can just like take this and plug it in right there. And then cross the that's the same. So I bring down outside. R this R across with that. Nice. Now I can monster for you guys. Cross product too. Yeah, like determine. Oh, okay. Alright. Did you cross products? I guess for moments and stuff. What was the cross product?
We're doing physics now as well, though.
Yeah. Third one is K. Because if you're rotating in one plane, all your momentum is along the K direction. Yep, and that would be like the momentum It's a lot of stuff. Pull out of the attic. All right, so I saw some people taking, like, jumping in, taking cross products, other people kind of staring at this equation like, what the heck? Where did this come from? So like this, let's get some highlighter action. So these are the same two terms. Like this position with respect to O prime, that is RER. Like That's just how, at least how I defined it. So if you're kind of following along the same process, then you did that too. You defined position as RER. And then this velocity is this term. Like those are the same thing. So HO prime is, I'm going to pull the M out here because the M is a scalar, so it doesn't really care what the cross products are. RER crossed with R dot along that ER plus R theta dot E theta. And that's kind of like the first step is just recognizing like, all right, yeah, I have two vectors and I want to take the cross product between them, figure out how big that is. So however, I saw a lot of people kind of go through this method, but then sort of they're like, oh, but it's 2 by 2. But like we do have a third dimension. It's just like some kind of out of plane, like a K, some kind of K, like out of the page dimension. And my first vector would be R and a 0 and a 0. And then next one is R dot, R theta dot, and a 0. Is this how, so it sounds like this was statics, how you do cross products. And then you take determinant that way. And then which one? Oh, sorry, just nightmares. Where? Oh, was there another class where this is like how cross products are done? More? Which ones? Calc 3? Yeah, calc. Okay, that would make sense. I'll show you how I like to do cross products. If you like it, you can use it. If not, don't worry about it. I usually write down the unit vectors that I'm working on in a little loop. If it's clockwise, it's positive, counterclockwise, negative. And if it's the same thing, ER, 0. So I'm going to get rid of this. So I have MR, ER crossed with, MR and R dot, ER crossed with ER, 0, plus MR, R theta dot, ER crossed with E theta. So that first term is 0. This term turns into a positive K because I went ER to E theta, turns into K. So MR squared theta dot in that K direction. And whether or not you think that like circle method is easier or harder than cross products, I don't know. If you like it, you can use it. If not, you can do any cross product method you want. You could even plug it into like a symbolic algebra solver and say, like, give me the cross product. Cool. So the last step is we want to show that this angular momentum, so for this, we know that this is constant because the sum of the moments around O prime are 0. which is equal to the change in that HO prime. And this, so this function that we just did, this mr squared theta dot, that's true for any system, like whether there's a spring attached or it's just like moving in a straight line, like HO prime is always mr squared theta dot, at least for rotational coordinate system, if you're describing things with theta and r. That's just the way to describe two-dimensional angular momentum like that. So then the last step is E. We want to show that although HO prime is constant, HO is not constant. So what do we want to do for that? How do we show that it's not a constant value? I'm just going to scroll back up. So right now, yeah, so we did this, we did this. But the question is, so we know that sum of the moments around O prime is 0, so angular momentum around O prime is always a fixed value. It's just, it is what it is. But then around O, we know that, we don't know, well, do we know? I mean, what do we know? What can we figure out? We want to show that it's, that angular momentum around O is not conserved, that we don't have like conservation around that other reference frame. What do you want to do for that? Yeah.
We just do the cross product again and see what we got there.
Do cross product again? Yeah. What cross product should we do?
Just use the value for the charge jump in B so that.
Okay, so we could say like PO crossed with MVPO. We could try that, right? So we could try that cross product. Yeah. Can't. So somehow, I mean, yeah, you can take cross products between any vector, but
Well, so you have the in the right like unit vector is orthogonal.
yeah, so that E1 somehow we got to get that E1 into like either ER and E theta or deal with it like out on its own, right? Like figure out what is ER cross E1 cross ER, E1 cross E theta. So one way we can do that. We can do it like visually of ER crossed with, sorry, E1 cross ER. It's gonna have something to do with like sine of the angle, right? Sine of theta. Because I think in not infinity. Like if you have two vectors, you can say it's magnitude 1 times magnitude of the other times the sine of the angle between them. So we could do that for ER and E1 that way. So it'll either be sine of theta or sine of theta minus 1. You want to think about it that way. It's a nice part about like unit vectors. They're all magnitude 1, so it's always some sines and cosines that way. Yeah, and if I have like E1 cross E theta, it's like theta plus 90, kind of looking at that total.
Where's the pi over 2 coming from?
So E1 points, let's do it down here. E1 points this way, E theta points that way. But this is theta, and this is,
Oh, it's the
yeah, like 90 degrees. Trying to describe like this kind of parallelogram. Yeah, really. If you add pi over 2, that is a cosine. Or no, subtract pi over 2 cosine, add pi over 2 negative cosine.
literally different.
Out of time. Okay, out of time. It's been fun, but get there next time.